This is Module 7.2, the electrolyzer model. The electrolyzer can appear intimidating, but the concepts behind the design are simple. To learn how the electrolyzer functions, we'll construct a model. We've talked about the 6 components of the electrolyzer. Now, to make the operation more clear, we'll develop a model to show in detail how they work together. Here's a schematic of our model electrolyzer showing all 6 components that we've talked about. This isn't drawn to scale, but is just intended to show how all these parts work together. So as a first step, we've turned on the rectifier. This results in 12 volts being applied across each of the cells as shown, and we set a current flow of 150 amps. Our cells are filled with electrolyte, and the voltage and current are sufficient to start splitting the water molecules into hydrogen and oxygen. As the oxygen is generated, it exits the cells and enters the water seal. The water seal acts to equalize the pressure in the cells and to isolate the oxygen and hydrogen from each other. We don't need the oxygen, so don't need to do anything with it, and as it leaves the water seal, it simply vents into the room. In the same way, the hydrogen gas exits the cells and enters the water seal. From the water seal, the hydrogen flows into the low-pressure gas holder. The gas holder bell is floating in water, and as it fills with gas, it will rise in the chamber. The compressor connects to the line running to the gas holder. The compressor starts to draw out the hydrogen from the gas holder bell and pumps it into the storage tank. After the gas goes through the compressor, the lines and storage tank are at a high pressure, and we can emphasize that with a change of color for high pressure. So here's a complete gas flow model for a simple electrolyzer, from gas production to the high pressure storage tank. Now we're going to add some valves to enable flow control and component isolation. First, to enable routine testing of the purity of the hydrogen gas, there's a hydrogen sampling valve on the line going from the cells to the water seal. As the hydrogen leaves the water seal, a two-way valve, the gas holder vent valve, determines the path of the hydrogen gas. In normal operation, we would direct the gas to go to the gas holder. But during testing and maintenance, we might want to direct the hydrogen gas to vent outside. The compressor inlet valve controls gas flow into the compressor. Now we can take the compressor out of the flow system for maintenance and testing. On the outlet side of the compressor, the tank filling valve controls whether the compressor is connected to the storage tank. We also need a way to fill our balloons. We put a balloon filling valve on the high pressure line to the storage tank and run a line to a second valve, the inflation valve, located near the balloon so we can safely control the rate of flow. A manual gas holder vent valve allows maintenance staff to empty the gas holder if needed. If the bell rises up to the very limit of its range, it exposes an internal gas holder vent line, shown here as a dashed line. This acts like an overflow line, allowing excess gas to automatically be vented outside. Now we'll add some switches to manage the hardware and to provide safety features. Switches on the gas holder control the compressor. When the bell rises to the top, the upper limit switch will start the compressor. As the compressor draws out gas, the bell will drop to its lower limit and the lower limit switch will stop the compressor. The high pressure switch monitors the pressure in the line and the storage tank. When the storage tank is full, the switch activates and first turns off the compressor and then reduces the current in the rectifier to an idle setting to reduce the amount of gas being produced. The pressure differential switch, the PDS, detects any sudden pressure drop in the high pressure lines, for example from a leak, and turns off the rectifier, stopping any further gas production. To reset this switch back to normal operation, there's a PDS reset valve that equalizes the pressure on both sides of the switch. The low pressure switch is located in the rectifier cubicle, but monitors the gas pressure in the gas holder. If the compressor should fail to turn off, for example due to a problem with the limit switch, the compressor will try and suck all the gas out of the gas holder. The low pressure switch will detect the negative pressure and turn off the rectifier. Now we're adding pressure gauges to help monitor the performance of the system. There are 3 high pressure gauges located at the compressor, the PDS switch, and the storage tank. These gauges allow us to monitor the operation of those components. At the water seal, the pressures are very low and require a different kind of pressure gauge. The inlet manometer measures the pressure of the gas from the cells. The outlet manometer measures the pressure in the gas holder, provided the gas holder vent valve is directed to gas holder. If the gas holder vent valve is directed to vent, the outlet manometer shows 0. We now have the basic equipment model. There are additional valves, switches, and gauges associated with individual components, like the cells, compressor, and storage tank, but they will be discussed as we examine each component in more detail. So here's the complete and simplified electrolyzer model. Our model has accounted for all the controls, valves, and switches visible on the front of the electrolyzer. This completes the electrolyzer model.